podcast is brought to you by LMU Munich.
Join all the previous speakers in thanking the organizer for all the hard work they put in this really perfect organization of this conference. My first time in this beautiful city. And also I thank them for giving me the opportunity to speak. So I will report on work done in the last couple of years with Abhijit Gadde, Davide Gaiotto, Shlomo Razamat, and Wenbin Yan. The title comes from a recent paper with Gaiotto and Razamat, but I will also talk about some of the previous work. So as elusive as supersymmetry is proving to be at the weak scale, this is a golden age for supersymmetric quantum field theory and for formal results in supersymmetric quantum field theory. And some developments have already been reviewed in previous talk, in particular John Schwartz's opening lecture reviewed a lot of the background material that I will need. And much recent progress stems from looking at a new class of observables. One places the theories in rigid backgrounds, which are typically products of squash fields, often in the presence of supersymmetric defects. And the main discoveries are highlighted here: 6 equals 4 plus 2 and 6 equals 3 plus 3, by which I mean some really surprising mathematical physics connection between supersymmetric theories. In my talk, we will focus on 4 dimensions, and non-supersymmetric theories in 2 dimensions, which, at least heuristically, stem from the existence of this unique 2,0 theory in 6 dimensions. And we have really discovered a really vast landscape of new superconformal field theories. And so today I will focus on perhaps a less familiar 4D2D relation, which is a precise duality between the superconformal index of one of these 4-dimensional theories labeled by a Riemann surface and a topological field theory on the Riemann surface. So again, this T of C is one of these sometimes referred to as class S theories, where S means 6. It's the 4D theory that comes from compactifying the 2,0 theory on a puncture Riemann surface, and the index is a certain twisted S3 times S1 partition function, which I will review in detail momentarily. And you may be more familiar with the Aldai-Gaiotto-Chikawa relation, which relates the S4 partition function of the same theory with a conformal field theory, Toda conformal field theory for general rank on C. So you see we are replacing S4 with S3 times S1. In the process, we replace a conformal field theory with a topological theory. So we are looking at at least in principle, conceptually simpler version of the 4D2D relation because it's a topological relation. And there are many reasons why you may want to do this. Perhaps the one I would like to emphasize is the pragmatic one. So the index is really a very useful observable. It tells us a lot of information about these mysterious theories, and we would very much like to compute it. And again, this is perhaps an easier entry point to uncovering this 4D2D dictionary. And although there is a lot to do on the conceptual side, the practical problem is in some sense solved. What I'm going to present to you today is a complete algorithm to determine the index of any one of these theories by a uniform answer which relies on solving this 2-dimensional topological theory, even when the theory has no known weakly coupled 4-dimensional Lagrange. So let me now review the basic characters. Let's start with the superconformal index itself. You have a conformal field theory in any dimensions. You can look at it in radial quantization. And so in particular, in 4 dimensions, we look at the Hilbert space of the theory on the 3-sphere and compute the Witten index with the -1 to the f. Now, the Witten index will in fact diverge because there's an infinite number of supersymmetric ground states if you naively define it this way. And so you want to refine your counting by introducing further fugacities mu I at some parameters. In the exponent, I could put a complete set of Q-closed generators. And then by the usual arguments of states with different energy canceling pairwise, you can prove that this is an index, evaluate to 0 on long multiplets, and in particular, it tells us the most complete set of data that you can ever hope to calculate from representation theory alone about the protected spectrum of the theory. This quantity will be independent on the variation of continuous moduli. And if you prefer a path integral language where you're taking the theory as 3 times S1, where this S1 is the temporal circle, and twisting boundary conditions so to account for these fugacities. Now, today we will look at n equal to 2, superconformal field theory in 4 dimensions, and then the index is a rather sophisticated object which depends on 3 of these superconformal variables, which are in red here, and you can see they account for various generators of the superconformal algebra. So in particular, P essentially counts the spin around a direction, and Q the spin in an orthogonal direction, and little r and big R are the generators of the Cartan generator of the earth symmetry. Now, unfortunately, I don't have time to review this beautiful work in n equal 1 theories, particularly if the theory has only n equal 1 supersymmetry. You can still define a similar object. It's not even needed that the theory be conformal. In fact, all you need is an anomalous earth symmetry, and you find an RG invariant. And the most sophisticated checks of cyber dualities involve precisely this index. But in this talk, we will do n equal to 2, and we'll always only do conformal theories. Now, this brand new world of theories that come from 6 dimensions, the generic theory will not have a wiki-coupled Lagrangian description. But suppose that you look at one theory that does have a Lagrangian description, then computing the index is very algorithmic, because I just told you that the index does not depend on the couplings, so I may as well compute the weak coupling, at 0 coupling in fact, by simply counting the protected states, and I'm guaranteed to get a result that is independent of the coupling. So what you do, you enumerate the elementary fields of the theory, phi, psi, f mu nu, and calculate the index of each of these objects, and also assign them fugacity under the color and favor group. And then what you do, you count. So if an object is bosonic, it can appear in arbitrarily many powers, so you resum a geometric series. If an object is fermionic, it only appears once. And then you project onto gauge singlets by integrating over the gauge group. So at the end of the day, the index is given in very close form by a matrix integral. So let's do the basic example of counting, which turns out to be very crucial. Let's consider a single chiral superfield. Q is my complex scalar, and psi is my fermion. As it turns out, the only 2 letters that contribute to the index, because I have energy 0, are Q and psi tilde, and together with all their derivatives in the 1, 2, and 3, 4 direction. Remember, I had these P and Q generators that were counting angular momentum in those 2 orthogonal directions. So I look at this monomial, this is its index, but then I remember that I have to consider all possible powers of the same monomial. So I have a whole geometric series that resums to this thing. And similarly for the fermionic letter, I just have this bit. And so all in all, the index of a chiral superfield is a double product of this sort, and this object has a name in mathematics. It's called an elliptic gamma function. Soon enough, I will drop these P and Q labels, but remember, whenever you see a gamma, it's not the Euler gamma function, it's this complicated object. And if you have flavored symmetry, then you introduce flavor fugacities, for example, for SUN, and you get a product of such objects. Now, the other cast of characters I need to review are this theory that comes on 6 dimensions. And again, I don't really have time to go through into this dictionary in much detail, but let me remind you. So the Riemann surface CS has complex moduli. Those translate into the marginal gauge couplings of the 4D theory. In particular, if I look at a gauge group with coupling, holomorphic coupling tau, that translates into a piece of the theory where you have a long cylinder with gluing parameter q, which is the exponential of tau. The conformal factor of the metric does not have a 4D counterpart. We checked this with Beam, Bobev, and mathematician Stony Brook Anderson, and we gave a rigorous proof in the dual holographic theory at large n that this is the case. And if cylinders correspond to gauge couplings, the punctures, remember this surface has punctures, correspond to flavored symmetries. And in fact, the flavored symmetries are classified by the embedding of SU2 into SUN, so there's a whole zoo of different punctures that you can have. And the main statement of this brand new world of class S theories is that you can consider the generation of the surface where when cylinders become long, that amounts to a certain pair of Penzic position of the surface, and that's a certain weakly coupled frame of the 4D theory. And all these different weakly coupled frames are related by generalized S dualities, which are a vast generalization of the idea that n equals 4 SL2Z duality is related to the modular invariance of the torus. Now, in this talk, we will mostly focus on the two elementary building blocks, which is a single three-puncture sphere that, of course, has no moduli, so it's an isolated CFT. And if the punctures have two maximal flavor symmetry and one minimal one, two SUN and one E1, that corresponds to a single bifundamental hypermultiplet, whereas if all the flavor symmetries are maximal, that is Gaiotto's Tn theory, which for n greater than 2 has no weakly coupled Lagrangian description. And then AGT told us, Gaiotto told us that the S4 partition function computed by Peston, following work on the previous work by Nekrasov, is a Liouville-Toda correlator on C. And so the item I'm looking at today, it's this new red item. We will compute the S3 times S1 partition function, also known as the index, and claim its topological correlator on the surface. So here you have the index. It depends on these three conformal Fugazzi, Q, P, and T, but it also depends on the Fugazzi associated with the flavor symmetries. And so here in blue are the flavor punctures. You can imagine that A1, A2, up to AK are labeling the punctures. And so this is, you want to think of this as a topological correlator that does not depend on the conformal moduli, because those are associated to gauge coupling. The index is dependent of gauge couplings, but it does depend on the fugacities. Okay, so lightning review of what one means by topological quantum field theory. You associate structure constant to a three-puncture sphere, and you have a propagator associated to a two-puncture sphere. So in our context, we look at the basic building block, which is the index of the three-puncture sphere, one of these Gaiotto-Tn theories, expanded. Maybe if you prefer to go from a continuous to a discrete basis, we can choose a complete set of class functions where alpha labels irreducible representations of SUN, and then now this C alpha beta gamma are the topological structure constants. Similarly, there's a propagator, and the statement that the theory enjoys S duality means that you can cut in different ways, and that means that the structure constants have to obey an associative algebra. If I think of this as matrices, so if C alpha is a matrix labeled by alpha, within this is beta and gamma, this is the statement that C alpha commutes with C gamma. So what we can do, we can parameterize the index of one of these unknown theories, and in the generic case, and we expect to get S duality. Now, in the rank 1 case for SU2, when the cylinders are associated to gauging of SU2, we are in better shape because all those theories have perfectly explicit Lagrangian descriptions where the basic building block, the vertex, which is the three-puncture sphere, is nothing but a hypermultiplet with SU2 cube symmetry. And when you glue, you are gauging the diagonal SU2, and so you build in this way a graph, and the order in which you do it depends on which S duality frame you're in. So for example, remember these are one of these funny gamma functions, and in particular, plus minus means that I'm taking a product, so this is really, each of these objects is really a product of 8 gamma functions, so here I have a product of 32 gamma functions. This is the index of the basic, one of the simplest theories, SU2 with 4 flavors. So you have a 4-puncture sphere. I can decompose it in the S channel, decompose it in the T channel. I must get the same result. So this is a highly non-trivial identity obeyed by this integral. We checked with mathematics and then found that at Caltech there were some mathematicians who were working exactly on proving this type of identities, and they replied to our email instantly and said, well, how did you know about this? We proved it last week. So this is an active subject of mathematical research, and in particular this identity checks associativity of the basic A1 TQFT. Now, so that was easy because these theories have Lagrangian description, but what we want to do next is exhibit the structure constant for the generic rank, SUN. And what will be very useful, in fact, to solve for the whole problem at once. by, in some sense, bootstrapping this 2D theory. And in fact, we make a further generalization. We not only consider theories associated with the surface C, but we further introduce a surface defect, a codimension 2 defect in the 4D theory, which correspond to codimension 4 defect in the 6D theory. So being codimension 4 in 6 dimension, this object, which is in red here, the color coding I hope will be systematic, correspond to a special new type of puncture on the surface. So the blue punctures are flavor groups, and the red puncture is the fact that I've introduced this extra object, the surface defect. And in fact, the surface defects are of 2 types that can either wrap a big circle fixed by G12 in S3 or a circle fixed by J34, and both wrap the temporal S1. And so the reason why this is a useful step to do is inspired by Liouville theory, where it's known that introducing degenerate punctures, the degenerate operator in Liouville, is key to the bootstrap. This is the trick used by Teschner to recover the 3-point Liouville structure constants. So the basic claim, which is a bit technical, but it's in some sense the main result of our recent paper, is that to introduce a surface defect in the theory that didn't have a surface defect, what I do, I take the index of the theory that did not have the surface defect, and I act on it with a certain operator. You can visualize that by the process of fusion of this special puncture with one of the flavored punctures. So for example, here I'm fusing the red puncture with the blue puncture, and the fusion amounts to shifting these SUN fugacity in a rather complicated way that involves a sum over n terms of ratios of theta functions. And we were very pleased to learn that this is, in fact, a known difference operator. It's the basic Hamiltonian of the elliptic Ruenar-Schneider model. Now, how did we derive that basic claim? We introduced surface defects by an RG construction, which I'm going to explain the next slide. But before that, I need to try to emphasize a more general idea. And the idea is that the index has intricate analytic structure, in particular singularities in these complex fugacities, and we want to interpret a pole as arising from a bosonic flat direction. So the theory is on S3 times S1, so generically curvature terms will give a damping term that will forbid any divergence. But if you tune parameters in a certain way, then a flat direction opens up. And the flat direction is, the culprit of that flat direction is a certain operator with appropriate quantum numbers, and the direction is parameterized by the VEV for that operator. So physically, what you're doing, you're probing the theory far away in moduli space by making a VEV to a certain operator, and the intuition is that you now flow to the infrared. The flow is triggered by giving a VEV to a certain operator, and so the index of the infrared theory should be related to the residue of the UV index as you approach the singularity. And we can, in fact, make this twiddle sign very precise and give a precise prescription for how indices of theories related by RG flows are consistent with each other. So with that idea, we can now engineer the surface defects in the following fashion. I start from a certain theory associated with Riemann surface C. This is this circle theory here. And I enlarge it. I enlarge it by gluing an extra piece to it. An extra piece to it, you will recognize the 3-puncture sphere with 2 white and 1 black puncture. And that means 2 maximal and 1 minimal puncture. You will remember that this denotes the free hypermultiplet. So I'm taking a free hypermultiplet, engaging a SUN group to attach it to an SUN puncture of the original theory. And then the claim is that if you now move on the Higgs branch for this extra method that you attached, and if you do it in the naive way by just taking a constant VEV, you flow back to the original theory. So you have enlarged the theory, and then the RG flow with constant VEV brings you back. But now you want to do something a little bit more clever, where you introduce a VEV that depends on space. And then you don't flow quite to the original theory, but you flow with the original theory decorated by an extra surface defect. And a more physical way to think about this is you are gauging a U1 symmetry. So in fact, you can see that the flavored symmetry of the enlarged theory, the non-abelian is the same because I started with one white puncture and I still have one white puncture, but I have an extra symmetry, which is the U1 symmetry of the free hypermultiplet. And so that is parameterized by a certain flavor fugacity A, and you can think of gauging this fugacity A in the presence of phi Heliopoulos parameter that will force you on the Higgs branch, and then you can think of this as being vortex configurations that in the infrared leave you with the defect. So if I now use the basic idea that I was explaining in the previous slide, that singularities are related to the infrared index, all I need to do is extract the poles in these red fugacities. And you see the poles come, there's the vanilla pole who has r equals 0 and s equal to 0. That will simply remove this piece and give me back the original index. But if I now tune myself at this more interesting pole where r and s are integers, the claim is that extracting the residue, I find the index of the original theory, but decorated with this extra surface defect. And then it's a calculation to show that this extraction of the residues amount to acting with the difference operator on the original index. But now here comes the fun. I can repeat the procedure by attaching this extra piece to any of the blue punctures, and I must get the same result because the different ways of attaching are related by different pairs of the composition of the surface. Everything is topological. So that means that the fusion of this red puncture with any of the blue puncture must give the same result. And that's a very powerful constraint that, in essence, fixes everything. And so the idea is that if I diagonalize this commuting set of operators, by acting in different ways, I must get the same result. And that's only possible if the index is, in fact, a sum over diagonal representations for all of the punctures. And so by comparing with Whipple count frames, you can actually fix the punctures. And moreover, by a slight variation of the procedure, you can, so far I was focusing on maximal puncture, but a slight variation of the procedure will allow me to discuss also puncture with reduced symmetry. Now, so it should be clear that this solves the problem completely. In particular, if I want to know the index of a genus G theory with X punctures in this diagonal base, it's immediate to write it down. Now, in the full case where I have Q, P, and T, the answer is a bit cumbersome because these functions are not known in closed form. We have an approximation scheme in our paper. But if you take a certain limit when one of the fugacity goes to 0, then everything is very explicit. It can be written in terms of Macdonald polynomials. In particular, the structure constants are inversely proportional to the quantum deform and T deform dimension of the group. And if you take the further limit where Q is equal to T, Macdonald polynomials degenerate to Schur polynomials, and you just recognize the 2D theory to be a certain quantum deformation of 2D Yang-Mills in the zero area limit. In some sense, this was a natural thing to expect because everything in our index is a class function, so I can label the states by irreducible representations of the group. And what is the theory that you know that is labeled, whose states are labeled by reducible representation of the group? Well, of course, it's 2D Yang-Mills. And we get the Q deformation thereof. Now, the general QT case is a certain refinement of the story that I don't have time to discuss. And so we have this general guess that we can subject to many checks. In particular, we get the correct symmetry and enhancement to exceptional group in the expected cases. And one very brief mention, in a certain limit, the index reduces to the Hilbert series of the Higgs branch, and this has allowed these authors to compute the Hilbert series of the modular space of two exceptional instantons. So, in summary, from a pragmatic viewpoint, we have complete success. We have determined the superconformal index of all theories of class S with or without surface defects, and through a topological version of the HGT correspondence. Conceptually, I think there's more to do. These RS operators clearly hint at some more direct 2D interpretation because their rational theta function look like two-dimensional indices. It would be nice to recover our results by an honest localization calculation for Lagrangian theories, but keep in mind that the vast majority of our theories are not Lagrangian. That's really where the practical use of this is that we have now the protective spectrum of all the Gaiotto theories, class S theories. To be nice to extend this to n equals 1, and perhaps following the work of Nekrasov and Witten, this could be perhaps easier to derive from 6 dimension than the AGT relation itself. So conformal defects are useful, and enlarging the view to the whole space of theories is also useful because it allowed us here to do bootstrapping theory space and solve for all the theories at once. I'll have one last slide, which is more personal. So our work is based on the work of many people, but I think in particular we could not have got this far without the beautiful results of Francis Dolan, his results on superconformal representation theory, and his results, he was the first to recognize this elliptic hypergeometry hidden in the index. So I think it's a fitting tribute to dedicate this work to his memory.
Thank you, Leonardo. Any question? Sergey.
There are many types of surface defects which have different number of continuous parameters. For example, here you discussed the ones whose continuous parameters are essentially points on the Riemann surface.
Yes.
But there are also surface defects which have no continuous parameters at all. Do you have any guess what their index would look like?
I don't. So the surfaces that we naturally ended on are the ones that have a natural RG construction. So if you have a good RG construction for one of these rigid surface defects, then I'm sort of optimistic that this similar logic will lead to determining the index.